Thanks to the organising committee for inviting me here today and allowing me to present the story of the Oxford vaccine from lab to the global community. I like to start my talks with this slide a lot of the time, and it's really to emphasize that in my mind, vaccines work, and they are one of the most effective medicinal interventions that we've ever made. This is a very old but very informative infographic from Public Health England, and it shows the number of diseases before a vaccine was introduced and then the number of diseases after a vaccine was introduced. And it really brings home that vaccines do work and that they are one of the most effective medicinal interventions we've ever been able to create. But what are the types of characteristics that we as biologists, vaccinologists, and immunologists need to consider when we're making a vaccine? Well, first and foremost, we need to make a vaccine that is tolerable. So we don't want side effects that are so severe that they're worse than the disease we're trying to protect against. Ideally, we want protection against severe disease. So we want to protect against hospitalization and death. If we can, we'd like to prevent against transmission and asymptomatic infection. But first and foremost, we must protect against death and hospitalization. We'd like that protection to be sustained, so long-lived. And in doing so, we need to be able to induce an effective immune response. So we need to be able to induce both a B cell and a T cell immune response. And those are the two key parts of your immune response that will mediate a really strong response towards an invading pathogen and be able to clear it. One thing that I didn't consider very often when I started my journey some 20 years ago were the practical considerations about vaccines. And these days they are first and foremost in my mind. And the thing that I think about a lot is the cost, because there's no point in developing a vaccine for a disease that is impactful in low and middle income countries if those countries can't afford it, if they can't get the vaccine to be able to protect their populations. You also need a vaccine that is stable. What do I mean by that? You want a vaccine that has got a long shelf life, so we don't have to keep making new batches. You want to consider how the vaccine will be delivered. So, I mean, whether you're going to give it in the arm, whether you're going to give it up the nose, how you're going to get it into the person, because this has a big impact on the cost of the vaccine. You also, as I've mentioned already, need to consider the side effects. Whether the vaccine will be tolerable and not cause too many reactions. The thing I want to touch on very lightly today is vaccine hesitancy. And just to mention that vaccine hesitancy and vaccine reluctance is nothing new. It's been around since the 1700s, 1800s, and this is a cartoon of that day showing Edward Jenner, who's frequently referred to as the grandfather of vaccination. And Edward Jenner noticed that milkmaids who were exposed to cowpox did not go on to develop smallpox. And smallpox is a hugely impactful disease, having killed some 300 million individuals. And what he did was a rather crude, rather simple clinical trial back in his time. And he infected individuals with cowpox and then went on to see if they caught smallpox, and they didn't. So this vaccine was then mass produced and started to be rolled out. And people back then were even worried about, there was a degree of vaccine hesitancy. And they were worried that if you were to get this cow-derived material, that you would go on to develop bovine-like characteristics. Of course, that is untrue. And in the late 1970s, early 1980s, smallpox was eradicated through vaccination. Here in the UK, in 2016, we were granted a measles-free status, but due to growing vaccine hesitancy and vaccine reluctance, we lost that measles-free status in 2019. So vaccine hesitancy is something that we really need to discuss. We need to listen to an individual's concerns and try to assuage them so that we don't get a situation where we have a large proportion of the population too scared to take a vaccine.
If I may come in there, sorry, just if I may come in there, just on the vaccine hesitancy, I think it would be very useful, particularly I think for our audience, particularly those also from the Muslim world. And there are famous stories. For example, I can give you a positive story and a negative story. The positive one was Queen Catherine the Great from Russia. She encountered vaccine hesitancy and she went. She inoculated herself, and as a result, of course, she became immune. And then her counterpart, the Caliph, the Ottoman Caliph of that time, despite the fact that in Muslim culture, inoculation actually was quite advanced and they were quite used to it, but for some reason he was listening to some silly advices, let's put it that way, and thought that, as you put it rightly, I mean, you don't want to inoculate yourself because why would you put germs into your body and that sort of thing? And as a result, he didn't inoculate himself and he died as a result of that vaccine hesitancy. So that's an example. It's I thought very interesting example to come up with from examples that we've actually had from the Muslim world. It's not a new thing, as you said, quite rightly so. And I think the fact that Edward Jenner, for which you are based now at the Jenner Institute in Oxford, was emblematic of that is actually quite interesting. Wouldn't you say so then, Tess?
I would agree. There was and I think there's a responsibility on the healthcare professionals and scientists and anybody who's medically trained to try and communicate these types of stories to individuals who may not have heard them before, who may have very genuine and very real concerns. And if you engage in those types of conversations, you generally can help individuals be less doubtful and less worried about getting a vaccine. And it's a very different scenario being vaccine hesitant to being anti-vax. I tend to engage with vaccine hesitancy far more than I do anti-vaxxers. But
wow, that's good to know. Yeah. And by the way, ladies and gentlemen, you're most welcome to send in your questions, because I'm having a conversation with Tess here, and the questions will be sent on to me where I could basically bring it up to Tess's attention, particularly as we go through her presentation there as well. Lovely, thank you, Tess. Yeah.
So the Ebola outbreak it started in 2013, 2014 in Western Africa. And at that time, the WHO and other government bodies generated a hit list, or a list of likely culprits that might cause another pandemic or another outbreak in the future years. And they listed a number of viruses, some of which you will have heard of, including Nipah, and some you may not have heard of, such as Crimean Congo hemorrhagic fever, which is a bit of a mouthful. But what they did list was disease X, and disease X was the unknown. It was the virus that might come from an animal or might come from an unknown reservoir, where we wouldn't have a vaccine against it. So what we did at the University of Oxford was start to make vaccines against all of these pathogens. And we tried to get a platform technology, so a platform technology that would be ready when we knew what disease X was. So essentially a technology that we could rapidly make a vaccine against any unknown pathogen. So within the University of Oxford, we use a lot of different types of technologies to make vaccines, but the one that I thought I'd touch on today, because it's consumed my life across the last 18 months, are viral vectored vaccines. And viral vectored vaccines are vaccines that are based on viruses that most of us will have seen before, and that are modified so that they're safe and they can be used as a platform technology. They can be recombinant live attenuated or replication deficient viruses. So the ChAdOx1 nCoV-19 vaccine is a replication deficient virus. They can be DNA viruses or they can be RNA viruses. The ones that I regularly work with are pox viruses and adenoviruses. And the reason that I like to work with adenoviruses are manifold, but one of the reasons is that it's relatively easy to manipulate and produce. And that means that we can get far more doses per liter of tissue culture, and you can get high levels of transgene expression. Now, what does that mean in English, essentially? It means that when you are confronted with disease X and you don't know how to make a vaccine, what you do is a little bit of investigative work. You try and figure out from that pathogen which part of it you think, if you had an immune response against, you would be protected from disease. So for example, for SARS-CoV-2, there's a spike protein on the outside of the coronavirus. And that spike protein is how the virus gets into your body. So what we did was we thought that if you took this small part of the coronavirus, and if you were to make a vaccine based on it and generate antibodies and T cells, you would essentially stop the infection in its tracks if you got exposed to coronavirus. So in early January, the sequence for the coronavirus was released. And myself and a colleague took that small sequence, essentially a recipe for making a small part of the coronavirus, and stuck it into the backbone of our platform technology. So what that means is when you get injected with the adenovirus, this very, very tiny part of the coronavirus will be expressed in your body. Your immune system will recognize it as foreign, and it will mount a really strong immune response towards it. So you'll get antibodies and T cells. And antibodies will bind to the outside of the coronavirus, these neutralizing antibodies, and stop the coronavirus from getting into your body and mediating disease. T cells are almost like the second wave. What they do is they will recognize cells that have become infected with coronavirus and destroy them. So you're inducing a really potent immune response against this small, tiny part of the coronavirus, the spike protein. So another advantage of adenoviruses is they've got enhanced stability. So that means they've got a relatively long shelf life and they don't need extensive cold chain storage. So they only need refrigeration. Now, there are obviously disadvantages with this platform technology. And one of them is that everybody in the audience will have been exposed to adenoviruses before. They cause a mild disease, a little bit of a cold in your upper respiratory tract. But that does mean that everybody will have seen them before. So we'll have an immune response to essentially the Trojan horse that is carrying in the small sequence of the coronavirus. And unfortunately, that can mean that you don't get a strong response towards the spike protein. So one way to get around this is to use an adenovirus that most of us will not have seen, so from a different species. And that's what we've done. We've used an adenovirus that has come from a chimpanzee origin. So the reasons that we like adenoviruses is they have low reactogenicity, so they've got relatively mild side effects. They induce a protective immune response that is long-lived. They can induce antibodies and T cells, and the practical considerations are favorable. So the cost of these viral vector vaccines is relatively low, especially compared to some of the other technologies. They're stable, so they've got a relatively long shelf life, and the delivery, we can give them intramuscularly, intranasally, subcutaneously, and intradermally.
So, Tess, can I ask a rather cheeky question then, since you pointed out enhanced stability through the adenovirus method here? Does that mean then that for those who've had the Oxford AstraZeneca vaccines, might they require boosters? Like, we've heard announcements just yesterday that Pfizer will probably, will require a booster, for example.
So that's actually one of the areas that I'm working on in the lab. So what we have done is we've given a third dose of the Oxford AstraZeneca vaccine to a small, relatively small, in the hundreds of individuals. And what we're looking to see is whether the immune response is boosted. And we have seen that with a third shot. But I think the question you're really asking me is, do we need that? Do we need the third shot in individuals? And I know that in some countries, including within the UK, they are actively considering that policy. Right. My interest would be to get first doses across the world to individuals who haven't had any vaccine yet, before we consider boosters. I think there's an onus on us to make sure that the world is protected before we start looking to deliver boosters. But that's not to say that boosters may not be needed, especially for individuals that are older or maybe immune compromised. We may need to give them boosters. But certainly at the moment, we're not seeing evidence, especially with the Delta wave within the UK, that we need booster vaccinations just yet. So my preference at the moment would certainly be to get first doses into those individuals most at risk around the world.
Fascinating, yeah. Thank you. Oh, by the way, I should have mentioned that it appeared like you were playing with Lego when you were working with the adenovirus there, building the vaccine.
And my children love Lego, so yes.
Lovely. Thank you, Tess. Yeah.
Not at all. So what I thought I might do is bring the audience and remind myself as well about the normal development process and timeline of making a vaccine, and to explain why we don't normally do it so rapidly as we have across the last year and a half. So normally we will take our time making a vaccine, designing it. We don't typically do it over a weekend. We will then progress the vaccines that we've designed into small animal studies. So into mice and other types of small animals. Depending on the results we get from the animal studies, we may go back to the drawing board and redesign the vaccine. These are relatively low cost experiments when you consider the later stages of making a vaccine. Once you've got a vaccine that you're happy with, and that's generally when you've seen protection in animal studies. So that's where you've vaccinated animals and then you've challenged them with the appropriate pathogen. You will move on to making a GMP batch. And a GMP batch of vaccine is a batch of vaccine that is manufactured that is far more pure than the vaccines that you would have used in these studies, so that it can go into humans. And we have an on-site GMP facility within Oxford, but it will still cost in the region of $1 million to $1.5 million to make a small batch of vaccine. And certainly for me as an academic, that's a lot of money. We then go on to phase 1 clinical trials, and these are small clinical trials with a relatively small number of individuals. And then depending on favorable readout, we will progress along into phase 2, phase 3, and then hopefully onto licensure. But at each of these steps, it becomes more costly. There's a lot more money invested, and that's typically why a vaccine development program will take 5 to 10 years to go from vaccine design through to licensure. And that was certainly the path that we were looking at when we started making a vaccine for a different coronavirus. And this was pre-SARS-CoV-2. And the coronavirus that we had made a vaccine against was Middle Eastern Respiratory Syndrome. And this is a coronavirus that is associated with a high level of morbidity and mortality, but luckily has not spread as far or as wide as SARS-CoV-2. The natural reservoir for MERS is the camel. And what we did was we identified the small part of the MERS that we thought would mediate, if we had an immune response, might mediate protection. And again, that was the spike protein, the protein on the outside that allows the virus to get into your body. And we made a vaccine, and then we tested it in small animal models, in rhesus macaques, and we also tested it in camels. And what we were able to demonstrate is that these animals had an immune response against our vaccine. And when we exposed those animals to MERS, they were protected against disease. So this was really encouraging, and it allowed us to move into a phase 1 clinical trial of our ChAdOx1 MERS. And we started that in March 2018, and we had 3 different doses of the vaccine that we tested in volunteers. A low dose, intermediate, and high dose. And what you're looking for in these clinical trials is safety, essentially. But you also always try and see if your vaccine is inducing an immune response and the type of immune response that you think might protect you against disease. And we saw that individuals were getting antibodies. So these are the molecules in your body that will clamp onto the outside of the virus and stop it getting into the cells. And they also act in other ways to help prevent infection and make the disease less severe. And we also got T cells. So this was very encouraging and allowed us to also start a small phase 1 study in Saudi Arabia with Chimark. And we had planned to do a 2-dose study as part of our phase 1 clinical study, but then SARS-CoV-2 came along, and all clinical trial activities were largely put on hold while we worked on the ChAdOx1 nCoV vaccine. So I thought I'd bring you through this just in very quick whistle-stop tour, as I've talked to most of the advantages of the vaccine when it comes to being a platform technology. So as I've mentioned, it's a non-replicating adenovirus. It is derived from a simian or a chimp-derived adenoviruses, so there won't be a large degree of pre-existing immunity in the general public. Um, we have the vaccine antigens, so the spike protein of the SARS-CoV-2 is encoded on the inside. Some other vaccine manufacturers like to display the antigen on the outside, but we encode ours on the inside, which means it gets expressed in your body after injected in the arm, and it induces a strong B and T cell response even after a single vaccination. So prior to April 2020, we had done 12 phase 1 studies and had vaccinated over 300 individuals with the ChAdOx1 platform. But adenoviruses had been used in a large number of people before this, and some 6,000 subjects, and they had a consistent reactogenicity profile with relatively mild side effects. And we demonstrated that ChAdOx1 MERS had been protective in non-human primates, and we'd started a phase 1 trial in the UK and the Kingdom of Saudi Arabia. So I was relatively confident over that weekend that we could make a vaccine against SARS-CoV-2. I wasn't relatively confident if we'd get efficacy or not, because we needed the clinical trials to really test and see if we were going to get protection in humans against the disease. But a large part of my life across January all the way through to April were consumed with trying to get the animal studies set up and to run those as fast as we could so we could go into our phase 1 clinical trial. And how did we do this so quickly? So if you remember the slide from earlier, each of these steps happened sequentially. And what we did was we knew we had to go fast. We didn't know it in, I didn't know it in early January, but we knew we had to try to go fast. Because certainly in early January, we didn't know how devastating this disease would be. Mm. So what we tried to do was to stack each of those steps. So they happened in parallel. So all the normal procedures were followed. So all the safety readouts, all the interactions with regulators, all the monitoring committees were engaged. We did all of those steps as you would do normally. But what we did risk and where we did take a big gamble, if you will, was financially. And that was AstraZeneca and Serum Institute as well. Because at this stage, we didn't know if we had a vaccine that would work, that would be effective. So a large amount of money was invested in these different stages before we knew we had a vaccine that would be effective. So I have to give a sincere thank you to our partners, including the UK government, who allowed us to go so rapidly by providing the funds to make this vaccine.
I think this is an important point, Tess. I think for those who, suffer through vaccine hesitancy, I mean, they may wonder because, you managed to do this so quick. Did you cut corners, for example? Yes. I think this is your chance to make it clear that no, have we cut any corners? I mean, what would you say to that? Those who are skeptical of, how fast you went, and then, as a result, maybe you were being economical there.
Absolutely. And to be fair, I can completely understand that criticism. And I would have to say that if anything, there was more engagement with safety monitoring boards. There was more engagement with oversight committees to make sure that we weren't cutting, and not that we would cut any corners, but we had more regular meetings. One thing that I have to say a huge thank you to those committees and the safety monitoring boards. Normally, those monitoring boards would meet in set sessions, so they might meet once a month or once every 3 months. Right. But what they did was they met more rapidly and more readily. And we had a very open and active dialogue ongoing with those committees. And we were obviously completely transparent throughout all of the trials. So a sincere thank you to all of those individuals who gave up all of their time so willingly. And the only risk that we did take was the financial risk. And luckily, that wasn't my financial risk because I certainly didn't have enough money. But it is, pardon?
Yeah, not your money.
No. It is a very important point to get across, that this isn't it is so, and that's why I do these slides. We did everything that you would normally do that would take 5 to 10 years to get a vaccine through to licensure. We just did it in 6 to 12 months. And that's why I didn't see my children or my family for a lot of 2020 going into 2021, because there's so many people working, not just me, the whole team. We're working every day for long hours so we can push this through as quickly as we could without taking any shortcuts. And in fact, I would say,
thank you. That's a wonderful, I think, for the ministers who are here listening in today, I think on the policymaker side, I think it's a good lesson, particularly for countries like Malaysia and others as well, where the bureaucrats can meet more than once a month, so it's, requires us to basically change things. Necessity, as Plato would say, is the mother of invention. Well, thank you, Tess. That's an excellent sharing there of the juicy bits of how you had to deal with the bureaucrats and the politicians. Thank you.
Not at all. And they were, I do have to give them a sincere thanks because they were so willing, because certainly at the beginning, we didn't need to go, we didn't know we needed to go fast, but at this stage, we knew we needed to go fast. So, and just to give you a little bit of, it's probably a little bit of insight into how careful we were. So before you start your clinical trials, you do some animal studies. And there was a preoccupation in the field at the time, rightly, that the what had previously been seen in some animal models with certain types of vaccines against SARS-CoV-1, so for example, whole inactivated vaccines, was this adverse event where you got vaccine-enhanced disease. And it was only in animals that this was seen, and it was only in experimental vaccines with SARS-CoV-1. Where when you vaccinated these animals and then you exposed them to the pathogen, they got worse disease than those animals that were unvaccinated. So we were super, super careful to test our vaccine across a large number of animals. So we tested them in mice, ferrets, monkeys, pigs, to both check that the immune response that we were getting was the right type of immune response and wouldn't be associated with this type of vaccine-enhanced disease. And then to also see what the outcome was after challenge. And some of the results that we got, particularly this seminal study with our collaborators in Rocky Mountain Labs, demonstrated that none of the monkeys that were given this vaccine and then challenged went on to develop this vaccine-enhanced disease. And in fact, we were really pleased because we were able to demonstrate that we prevented pneumonia. So this was in March, April time of last year. And as I said, we went through an awful lot of animal studies, being overtly careful to make sure that we were not seeing these types of immune responses that might result in vaccine-enhanced disease. And we didn't. And that allowed us to start our phase 1 clinical trials on April 23rd last year. And I do remember it very clearly because I remember walking home that night after the first 2 individuals had been vaccinated. And it was a very surreal feeling because at that time the streets were very quiet in Oxford in the UK because of lockdown. And having known that we developed and pushed through this vaccine and it was in an individual's arm was a very surreal moment in my life. Regardless, so we started relatively small. We started with 1,000 individuals and they were randomized. So what that means was approximately 500 individuals were given the ChAdOx1 vaccine, and then 500 individuals were given a control vaccine, the MenACWY vaccine. And what you're looking for is to then check in these individuals which group went on to catch more COVID-19, not that you would want large numbers of individuals to catch the disease. And at that stage, we only had a very small number of individuals that were vaccinated with 2 doses. That was 10 individuals that had 2 doses of the vaccine. And what did we see? So I'm going to bring you through just the top line, very interesting data, hopefully. Well, I was certainly interested in it. And this is the reactogenicity profile. So what that means is the side effects. And as you can see that after the first dose, there are more side effects. So a higher number of people had pain than the second dose. And the other thing that I want to take a moment to discuss is how we define disease. And we define disease, so we define symptomatic COVID-19 relatively, so it would pick up mild, moderate, and severe disease, the way that we've defined it. So it's a PCR positive swab, and individuals either had to have fever, cough, shortness of breath, a loss of smell, or a loss of taste. And this makes it a little bit difficult to compare across trials because not every trial uses the same defining characteristics of disease. So we've defined it such that we will pick up mild, moderate, and severe disease. Other trials will have defined it so that they only look for moderate and severe disease. So when you're comparing results, especially efficacy results across trials, you're not really comparing like with like because how we've defined disease and others differ. And that's true of most trials. So at the time when this trial had started, we were also developing the assays to try and measure the immune responses. And I have to give a big thank you to the team, especially the serology team, for developing these assays. So the next sets of slides will bring you through some of those assays. You don't need to necessarily read them. If you just listen to me, I'll bring you through the top line take-home messages. So this is a graph demonstrating individuals who got the MenACWY vaccine on day 0. So if they got the ChAdOx1, you would expect the antibodies. This looks at the binding antibodies. You would don't in the MenACWY, but they do in the ChAdOx. This individual here had obviously had COVID and hadn't known at that stage. So this was in April 2020. One dose on day 0 and then a second dose on day 28. And what you can see is that the antibodies went up even higher. So we were obviously very interested in this data and the animal data that we had generated that showed that 2 doses were better than 1. And that's one of the reasons why we changed to a 2-dose regime compared to a 1-dose regime. These are lots of very noisy graphs, but essentially the take-home message is that neutralizing antibodies, these are the antibodies that will bind to the outside of the virus and stop it getting into your body, are induced after 1 dose, but are induced even better or higher amounts after 2 doses. So again, that encouraged us to go to a 2-dose regime. T cells, so the part of the immune system that comes in and clears the infected cells and makes the disease less severe, they were not induced in the MenACWY as you would expect, but you did see the strong induction after 1 dose of ChAdOx1 nCoV. We didn't see a further boost when you gave a second dose, but because we'd seen the strong induction of neutralizing antibodies and binding antibodies, we went with a 2-dose regime. But who were those individuals that we thought we should focus on mainly? And they were older adults. Everybody knows now that age is a significant risk for morbidity and mortality after infection, and that you've got an increased frequency and severity of a number of common diseases, including influenza. And then vaccine developers have exploited a number of different strategies to overcome, to get a stronger immune response in older adults. So for influenza, the dose of the vaccine for older adults can be increased almost 4-fold to try and get an immune response that is as strong as you would see in individuals aged 18 to 55. Or you can include an adjuvant, and an adjuvant is something that helps tickle up your immune system. But other vaccines haven't needed those strategies, and we were really hopeful that our vaccine wouldn't need these augmentation strategies to boost the immune response in older adults. And what we saw in older adults was, so this is the reactogenicity profile, the kind of side effects you see in individuals aged 18 to 55, 56 to 69, and over 70. And you can see the size of these bars decrease with age. So that means the side effects are less frequent and lower in older adults, and again are less severe in on the second dose. When we gave our vaccine to older adults, the vaccine-induced antibody response after the first shot was decreased in older adults, but with a second dose, it came up to the same response in 18 to 55-year-olds. And that was largely seen as well in the neutralizing antibodies. And again, we saw a peak of T cell responses in 14-year-olds. So this again encouraged us that we had a vaccine that we could use in older adults and that we should use a 2-dose regime. So this is where I'm going to take a moment to try and bring you through some rather complicated vaccine efficacy readouts, because I think at the time in November last year, it was rather complicated, the messaging that we were trying to get across to individuals. And I don't know that we necessarily communicated it as best we can. So just to recap, the way that we've defined disease is with a PCR positive swab and only one of these following characteristics of COVID. So fever, cough, shortness of breath, insomnia, so loss of smell or taste. So in our efficacy cohorts, what we had were different types of vaccination regimes. We had 2 different types of vaccination regimes. We gave a large number of individuals a half dose as their first dose, and we call that LD. And then we gave them a standard dose. So that's this regime here, LDSD. And then with the second cohort of individuals, we gave them 2 full doses, so SDSD. And what we saw when we looked at the efficacy readouts was that individuals that had had this half dose followed by full dose had this 90% efficacy. And individuals that had the 2 standard doses had 60%. When you combine those 2 together, we got an overall vaccine efficacy of 70%. At the time when we were reporting, and there was an onus on us, there was a legal requirement that we needed to report these results as soon as we knew them. We didn't necessarily know the biological explanation as to why we were seeing these differences. We had our suspicions, but we didn't have the data to prove it. So what we were able to show with a little bit of time was that in these individuals, so the half dose followed by the standard dose, was that these people got the 2 doses with a longer interval. So there was a longer time between the half dose and the full dose. And that resulted in a higher level of binding antibodies. In the individuals that had 2 full doses, there was a shorter interval between those doses, and that resulted in a lower titer of binding antibody. So that was one of the reasons why within the UK and also the WHO recommended this long interval between the 2 doses of the Oxford AstraZeneca vaccine. What we saw when we did our final, this was only the interim efficacy that we looked at. When we looked at our final vaccine efficacy against death was 100%, and overall vaccine efficacy after the second dose was in and around 67%. So this, to me, again, was a very, I remember being told these results and getting quite emotional on that day, and also then having to get the statistician to bring me through it all again, because I didn't necessarily remember all the numbers in the first passover.
Did you cry when you got the results?
There may have been something in my eye, but there was an awful lot of hay fever going around at that time in November.
Thank you.
So I wanted to bring you through this slide of my journey and the vaccine's journey across 2020. So myself and my colleagues started designing the vaccine on January 11th, 12th, when the sequence was released. I pushed through the animal studies through January, February, March, and then we started our phase 1 clinical trial in April 23rd. we partnered with AstraZeneca. I think it was in May that year. A large section of this year is quite discombobbled in my mind. I tend to get a large number of those dates mixed up. We started our late stage trial in Brazil and South Africa in June. I do remember November and December because they were very, very busy months when we were trying to get all the immune results that we needed to get that ready for the regulators, both in the UK and the EU. Those were incredibly busy months pushing through those assays and getting those samples shipped across the world. We announced our efficacy readout and we were authorized for supply in the UK in December. And that was a wonderful but surreal feeling, and still an awful lot of work to do across Christmas and New Year in December. So didn't get a huge amount of time off across 2020. And what have I been doing since? I'd like to say I've been resting, but that would be misleading for both me and my team, and actually all the collaborators across the world. Variants of concern have come along, and they've certainly kept a lot of us awake at night. And what we've seen and others have seen is that these neutralizing antibodies that I have described to you as being very important, they do decrease against these variants of concern with all of the vaccines that have been tested so far. But even though these neutralizing antibodies are decreasing, we're still seeing very good efficacy against disease. So we're seeing efficacy against the Alpha variant within the UK of about 70%. So that's really important, that even when you get the messaging through social media that the binding antibodies or the neutralizing antibodies are going down, yes, they are, but we're still seeing really good efficacy and impactful efficacy. And the type of efficacy that when you look at what's happening within the UK now, if you look at what's happening in the number of cases per 100,000 in the second wave within the UK and the deaths, if you look what's happening in the third wave, and this is the Delta variant that is ripped through the UK, you can see the impact that vaccination is having within the UK. And the vaccines that have largely been used are Pfizer and Oxford AstraZeneca. And this is a preprint that has come out from Public Health England that is showing the efficacy of these vaccines in the real world, so making a real world impact against hospitalization. And I have to say that for me, keeping our elderly, our most frail, our most vulnerable out of hospital is what I want from our vaccine. And if we can do more with it, that is great. But this is what making a vaccine is for me. And you can see that there's very little between these vaccines against the Alpha variant and also against the Delta variant. But ideally, you should get 2 doses. That does seem to have the most impact, but you're still seeing a real impact even after 1 dose. So Public Health England have estimated that vaccination has prevented over 50,000 hospitalizations in adults aged 65 or over in England, and that vaccination has prevented some 60,000 deaths. And when the early stages of this data were released in February and March of this year, obviously with lower numbers because the vaccines hadn't been in as many people's arms for as long, that data was very impactful for the whole team because you were able to see what your vaccine was doing in the real world.
I have a quick question from the audience here about the variants of concern test. I mean, it's an audience asking how far can the virus go mutating into more dangerous variants, So these variants of concern, such as the Delta variant, what's your sense there, Tess?
So the virus has to...
We have epsilon after this and gamma and all the way to...
Indeed.
Yeah.
So the way that the virus gets into your body is through the spike protein. So it can't mutate it so much that it changes so drastically that it can no longer get in. because then the virus will not survive. It will not, it's no longer the SARS-CoV-2 virus. I think there will be certainly what we've seen with influenza is that the virus will mutate to a degree. And then what it does is it almost rotates the mutations that it's used. So I think we will see more variants of concern, but at the moment, those variants are of concern for me. They're not necessarily, they were in the early days keeping me awake, but I've yet to see or hear of a variant of concern that is now making me an insomniac. Because the real world data that we're seeing is very encouraging so far.
Thank you.
So I wanted to touch on a little bit of the work that AstraZeneca have been doing in supplying this vaccine globally. They have worked with a number of countries, and we now have approvals and emergency authorizations in over 100 countries to date.
And Malaysia is one of them.
Pardon?
Malaysia is one of them, by the way.
Very good. I'm very happy to hear that. The more vaccine we can get into people, the happier I will be. All and any authorized vaccines. We late last week, I think it might have actually been Tuesday or Wednesday of last week, we had supplied more than 1 billion doses, or AstraZeneca had supplied more than 1 billion doses for supply in 170 countries. They have built more than a dozen parallel regional supply chains, and they're collaborating with 20 partners across different countries to supply this vaccine. This is an old stat, but so I'm not entirely sure if it remains at 80% vaccine supply. It may be slightly higher, but certainly at up to a month ago, we were AstraZeneca were supplying 80% of the total COVAX supply. So the global supply to low and middle income countries. And this is, I wanted to finish on a little bit of a data heavy slide because that's what I do for most of my day job. And this is to some data that we have recently generated in the lab. And I think it's especially important in countries that may have had their first dose, but are awaiting their second dose. And what we've done is we have looked at the immune response, so these total antibody binding units, so to see how many antibodies you have in individuals that are given the regime that is recommended by WHO and other countries, the 8 to 12 week. You can see that the antibody titers are around this level. And with longer regimes, so with an interval of 15 to 25 weeks, or even an interval of 44 to 45 weeks, you can see that the antibody titers go even higher. So in those countries where individuals have had a first dose and may unfortunately be waiting for a second dose, we know that this data is hugely encouraging because it suggests that we will be able to push those responses even higher. And I would like to end there with my slides. I have a huge team around and beside me delivering this vaccine, a huge number of collaborators, both nationally and internationally. But first and foremost, I need to thank the clinical trial volunteers, because without their bravery, and it was bravery in early 2020 because we didn't know whether these vaccines would work or not, but without those individuals coming forward and taking part in our trials, we would not have our vaccine for the world. And with that, I am very happy to take any further questions.
Great. Well, thank you, Tess. Wonderful, actually. And now, just for our continuing on our conversation as we go on throughout, and I've got a number of quite technical questions as well, clearly from specialists who are part of this international conference, Tess. Now, one is, why would we need to have a booster jab when we already have the memory cells that remember the same pathogen for faster antibody production in future infections? So I thought that's quite a reasonable question.
Yes, it absolutely is. It's so in certain individuals, those type of memory responses may not be at a level that could protect you against disease and hospitalization. So in older adults, it's certainly harder to induce, typically it's certainly harder to induce a long-lived memory T cell response, and you may need a booster there to help augment the not necessarily the memory, but the circulating T and B cells that could mediate protection.
Right, good. Now, here's another technical question. I mean, of course, I don't understand this, but here we go. So now, the Lancet, which is a major, of course, famous British medical journal, reported that the antibody level in humans will be reduced to more than 50% after 10 weeks, even with a complete dose of vaccine. So what is the actual explanation to this reduction of antibody levels?
So that's a very good question. And we are in a position where we have data looking at the longevity of antibodies and T cell responses. And we are trying to get that published as quickly as possible, because we don't see quite as drastic a fall off in the antibody titers or the T cell responses as others may have seen. And that may reflect different population cohorts, because I think that Lancet publication, I think the individuals within that there may be a proportion that were immune compromised, and we definitely do need to look and see if those individuals might need a booster vaccination. But we're hoping to get that data out as quickly as we can.
Yeah, thank you. Now, this is a question from the policymakers, particularly those in the Ministry of Health here, actually. What is your view, Tess, on getting different vaccines for the second dose of vaccination? Is it recommended if it is due to ADR, which is the adverse drug reaction experienced from the first dose of vaccine in particular?
So for the very rare side effects, so the thrombolytic events that have been reported with the adenoviral vaccines, there have been so the incidence of those tends to be relatively small, and it depends on the populations that you're looking at when you look at the incidence. There have been a recent number of publications, I can think of at least 2, that have shown those adverse rare side effects do not happen on the second dose, or if they do happen, they happen at a level that is common within a population. So it's not above the population level. And obviously, the other vaccines have very rare adverse reaction as well. I think when it comes to mixing vaccines, I've been involved in some studies looking at administering Pfizer first or Chadox first, and then doing the other second. One regime tends to is slightly more reactogenic, but the immune responses in the mixed regimes do look good.
Right. So, I mean, with sort of the news that we've been hearing, I mean, this cocktail vaccine is really like, you've had the Pfizer one first, and then some will then have an Oxford AstraZeneca, or the other way around. You've got the Oxford AstraZeneca first, and then you might have a Pfizer. I mean, that in itself is not problematic then, right?
Certainly, so where my bread and butter, where I like to, my stomping grounds are the immune responses. I'm not necessarily a policymaker, and I certainly would not like to try and think about the logistics of delivering those types of regimes, or getting them past regulatory, getting them licensed. But certainly from the immune aspects, they look good to me. The antibodies and the T cells look favorable. There may be a slightly increased reactogenicity with one of the mixing schedules. And certainly with the Chadox vaccine, you tend to get a bigger ow, if that makes sense, with the first dose than with the second dose. Whereas with the Pfizer and the RNA, the ow comes on the second dose. So I think you need to bear that in mind if you're going to vaccinate a large number of healthcare professionals who may then feel a little bit ill on their second dose, because that can obviously impact healthcare provision. But for me, as an immunologist, the data are encouraging.
Right. I mean, I remember when I had my Oxford vaccine, the first round, I mean, I was down for a few days. So that's the sort of anecdotal evidence. I mean, anecdotal accounts that most of us actually go down with for some fever, and I tell myself, oh, it's a good thing when I got this fever. That means it's actually working. Whereas
Absolutely
my
agree.
wife, she's a medic, so she got her Pfizer vaccine back in December, and she was telling me she didn't get, there wasn't any side effects whatsoever. She didn't, So then I sort of joked with her and said, well, are you sure this vaccine is working? You see. So, but Tess, it's interesting. I mean, Malaysia, for example, I understand certainly through the minister of vaccination there, Khairi Jamaluddin. I mean, he was telling me that actually they've gone for the route of trying as widely as possible, I think, in terms of the vaccine, so including using vaccine from the eastern side. I mean, not just the western world, but the Chinese ones, for example. So as I understand it, in Malaysia, for example, they have obviously the Pfizer, even the Moderna is now approved, and JJ, the Johnson & Johnson, of course, or the Oxford vaccine, but they also actually do Sinovac, which is a Chinese vaccine. And I'm hearing also that they are approving, or they are getting to approve the Russian one as well. Now, and then we hear stories about the Sinovac vaccine has about 50 efficacy, and so on and so forth. And so why do we have these differences? And I think, would you give the advice that I think if you have, you shouldn't start to pick and choose? You see, this is the thing that I think governments around the world are a bit worried if people start to pick and choose just on the basis of the vaccine's efficacy. If you look at Sinovac, the Chinese vaccine is 50%, then, Pfizer is 90%, then of course you think that you want to go for the 90%, but we were told at the same time we shouldn't pick and choose. So what's your sense there, Tess?
So that was one point I do try to make in my talks, is that you can't necessarily compare the efficacy across these trials, because the way that one trial defines its disease and a different trial defines its disease, they're not always directly comparable. And for me, what you need to look at is the real world effectiveness data, and trust the regulators and trust the safety monitoring boards, etc., to have made the recommendations in your country that are best for the country and best for the people. And my message, both to my family and my parents who were in a different country, is take the vaccine you are offered, get a vaccine in your arm, make yourself safe, and make the world safe.
Right. Wonderful. Well, I now this is I'm just gonna ask two last questions here. We're gonna wind down, in fact. But here's one question from a frontliner, a doctor. He says, "I'm already vaccinated. Historically, we needed about 7 to 10 years to refine any vaccine before we dare to inject into our body. Are the present vaccines therefore safe?" This is from a frontliner asking here in Malaysia. How would you respond to that?
I can understand the concerns, because I certainly worked in a field where it took me 5 to 10 years to make a vaccine. All the safety steps that we take to make a vaccine in 5 to 10 years, we did in 9 to 12 months. We just did it faster because we knew we had to. And we worked with it. We did all the normal testing. We did all the safety that you would do with any other vaccine. It just ended up with a lot of people working in a lot of hours to get these to the same level.
Wonderful. Well, now I have had hundreds of questions, literally, and I'm afraid we can't attend to all of them, because I at least need to ask my own question, actually. So if I may, the very last question, Tess, is from me. Now, could it be a new norm now, a new normal, that future vaccines will be developed within a 12-month time frame instead of a 5 to 10 years is normally required, like this frontliner doctor was just wondering about? What say you?
That's a very good question, and it actually it segues into something that concerns me quite a lot. We've learned an awful lot of lessons. The frontline healthcare workers, sanitation workers, the population, the communities at large. We've learned a lot throughout this pandemic. And I think there is a responsibility on us as a global community not to forget. And I know we all want to get back to normal, whatever normal is, but we shouldn't forget the sacrifices that we have made. And we should almost have an institutional memory, and we should not forget, because I don't want my children or your grandchildren to have to do what we've had to do across the last year and a half. I think there is a responsibility on the scientists, the regulators, the government, to ensure that when there is another pandemic, and there will be, that we are in a better situation so that we can make vaccines, therapeutics, track and trace, all types of interventions faster and better, so that we don't put such a burden on the future generations to have to go through what we have.
Very well put, Tess, if I may say so. I mean, really, we end on a very humbling note, Your Excellencies, ladies and gentlemen, there. And I think it really, I mean, inside, I'm a theologian, and I'm spiritually crying inside of me just to hear you, a scientist, to say that. I mean, even as a Muslim, we have something called fardu kifaya, which is a public duty, and it's marvelous to see people like yourself fulfilling your public duty for the sake of mankind. And I think, and I hope, ladies and gentlemen, that we can all see from this Oxford story, the Oxford vaccine, from the lab to the global community, how this story basically chimes well with the theme of our international conference, that modern research, that latest research, that ijtihad, that, that scientists have actually led to this innovation, this bid'ah hasana, this good innovation. And now, indeed, the rolling out, the practice, and the dissemination and in the implementation of that, and all of that underscores the need of the hour. And as Plato would say, indeed, well, necessity is the mother of all inventions. And it's really when people like Tess and her team have actually stepped up to really save the world. And for that, Excellencies, ladies and gentlemen, let us all give a very, very, very warm, even though we are in a virtual world, I know the clap will probably not be heard except by God for those, but it's certainly we all like to applaud you, particularly for this development of this Oxford vaccine, because it is almost free, it's done at cost, but to spend all those hours not sleeping at nights and so on and so forth to develop this for the sake of all mankind. Well, again, thank you, Tess, on behalf of all of us here in Malaysia and all over the world as well, all the way from Australia to the United States, India, Pakistan, the Southeast Asia. Thank you very much.
Thank you.
Yeah, mine.
Over to the organizers here. So.
Thank you, Yang Berbahagia Datuk Dr. Afifi Ikuti and Professor Teresa Lambe for such an inspirational session just now. Your Excellencies, distinguished guests, ladies and gentlemen, the keynote session just now brings us to the end of the opening ceremony. However, before we end, the organizing committee will now present an appreciation virtual memento to Professor Teresa Lambe. We are
I
very
told you,
honored.
Tess, this is the ritual bit. Even virtually, we have a present.
We are very honored to have you today to share your findings and experience with us. Thank you again, Professor Teresa. In addition, the organizing committee also would like to present a virtual token of appreciation to Yang Berbahagia dan Afifi for officiating the opening ceremony and moderating the session.
Thank you to the organizers. Lovely. Thank you to the organizers. Thank you.
Thank you, Dr. Afifi. On behalf of the organizing committee of ICPHS 2021, we would like to extend our appreciation to all distinguished guests, speakers, partners, sponsors, media members, and participants for attending the opening ceremony. Distinguished guests may now leave the ceremony. However, to all participants, please remain in the session for a short announcement.
Thank you very much.
Thank you.
We shall see you next week.
UniKL, kita datang. UniKL, jadi cemerlang. Universiti Kuala Lumpur mercu tanda pendidikan MARA. Sertai kami bagi pengambilan ke program persediaan diploma, ijazah dan pasca siswaza hari ini. Layari unikl.edu.my where knowledge is applied and dreams realized. are UniKL.
Ladies and gentlemen, we would like to announce once again that we have a breakout room for e-posters which can be viewed throughout the day. We are pretty sure that everyone needs a break. Hence, we shall now take a short tea break and we shall meet again in 15 minutes time. Thank you.